Alright, so let's solve problem 2 for homework 6 now. Let's start off with part A. So here first we need to set up a set of differential equations for our entire system. So let's start off by segmenting our equations to three different sections, and let's go over each section one by one. And so first of all, I want to treat the inheritance of the host. So this is kind of the first thing that we see is kind of coming out of this pump, and kind of is the initial part of our system. So let's write down an expression for this initial part. So as you guys know that the inheritance is kind of analogous to the to inductance in an electrical circuit, and for this part the expression would be given something like this. So whose inheritance, so we have the pressure different, and in this case we are looking at the pressure at this point over here, and then at this point over here, before and after the value of IF is given, right? So we would have PS minus P1, so that's the pressure drop, divided by, not divided by, that's just the pressure drop in this case. That comes later on, and this would be equal to the inheritance, so I hose times the derivative of the flow rate, or the rate of change of the flow rate going through the hose. So this is Q hose, this term over here. So the amount of flow going through the hose. And we can now rearrange this expression a little bit. And the reason I'm doing that is so that we can have our expressions easily written down in the matrix form, which will help us in for part B. So we have I hose dq hose dt plus P1 minus 0 dot h, and this term over here is something that you don't have in the original expression, but this h variable, which is the height of the tank, is another variable that will pop up in our next two equations, and is one of the variables that we need to model for in the current system. So we'll have these three variables making up forming the three variables of the system, and hence we'll require three equations for this entire system as well. So I'm just putting this expression beforehand, even though I've not explained how it will come about in the later expressions. We will look at that, but for now just keep that in, and that will just help you understand how this expression can be written down in the matrix form for part B. So that is our first equation. And now let's look at the next part in our system, which is this system over here. So we are looking at some of the flow that's going into this accumulator, and then some flow that's going through this first valve and entering our tank. So for this second part, we are now applying mass conservation near the accumulator. And what that is basically saying is that the flow that's going Q hose, that would be some amount of flow from the hose is going into the accumulator. So as you guys know, the flow rate going through an accumulator can be given by an expression that is the compliance of that particular accumulator times dp1 dt. So that's the pressure drop over there. So you would have, in this case it would be P1 minus 0, and you see that P1 is the pressure over here at this point. And then we would also have some of the flow that's going into the tank, and that flow is going through this valve R1. So one way of writing that flow would be the pressure drop before and after the valve divided by the resistance of that particular valve, right? So we can write it down as plus P1, that's the pressure before it enters the valve, minus rho GH, so that's the pressure at the bottom of the tank over here, and so that's the pressure that would be after the valve, and that divided by the resistance of the valve. So this is equation 1. This is equation 2. And now we want to rearrange this equation as well so that it fits that form that we are looking for. So in this case, it can be essentially written down as that. So we have minus Q hose that plus minus this is all equal to 0, and this is equation 2. So again you can see that we have our three variables, so Q hose, P1, and then finally H. So those are our three variables. And now we are looking for our third and final equation, and that would be applying mass conservation at the output here. And how can we apply mass conservation over there? So let's have a look at that. So this is also in a way looking at the mass of the water inside the tank, right? So we are looking at flow that would be coming in, Q in minus Q out is equal to mass stored, right? And this can be written down as, so what is coming in? The flow coming into the tank, as you guys know, is the same as what we had used for our second expression here. So P1 minus rho GH divided by R1. The flow going in through the first valve is the flow that's coming in. So we can write it down as P1 minus rho GH divided by R1. That is Q1, that is the Q in. And then similarly, Q out, what would that be? So that would be the flow that is going through our second valve here, right? And we can write that down as rho GH. So that's the flow that is going into the second valve. The pressure before the flow is going into the second valve, right at the bottom of the tank over here. And then minus P naught. The pressure that's outside, which actually turns out to be 0. So that term actually drops out later on. And this would be equal to the volume of water that's being stored inside the tank. And that can be given by the cross-sectional area of the base of the tank, which is A, times the rate of change of the height of water inside it, right? So dH by dt. And we can again transform this a little bit so that it fits the form that we are looking for. So in this equation, we don't have the Q hose term anywhere, so we have a coefficient of 0 multiplying it before that. So very similar to this 0 times H term that we did for equation 1. And then we would also have terms for P1 and P and H plus A dH dt plus rho g 1 by R1 plus 1 by R2 times H is equal to 0. And this equation over here is our third and final equation. So these three equations together form the system of differential equations which include the host compliance and the inheritance of the fluid, right, and kind of help us determine the governing equations for the system essentially. So now we can move on to part B, where they're asking us to determine the system transfer function from PS to Q naught using the method of determinants. So now we need to set up our matrix form of this equation, and before that we want to take the Laplace transform of these equations and then set those together. So the Laplace transform for all of these equations would be, so for equation 1, the Laplace transform can be written down as I hose times S multiplying your in this case, since we are taking a Laplace, maybe I should start using capital letters. So Q hose, right, plus P1 S plus 0 times HS, which is equal to PS. And then for equation 2, it would turn out to be minus Q hose S plus CFS plus R1 times P1 S minus rho G R1 HS, and this is equal to 0. And our final equation would be 0 dot Q hose S minus 1 by R1 P1 S and plus AS plus rho G times 1 by R1 plus 1 by R2 HS is equal to 0. So if we were to write this down in the matrix format, we would have a 3 by 3 matrix, right? So all of our coefficient terms would basically be just P1 here. In this case it would be just -1. In this case it would be that. In this case it's just negative rho G, 0 over here, that, and that. So those are our 3 by 3 kind of coefficients for our matrix. The 3 variables are Q hose, P1, HS, and on our right hand side we have P1, 0, 0. So our coefficient matrix would then now look something like this. S1, 0, minus 1, CFS plus 1 by R1 minus rho G R1, 0, 1 by R1 times CS plus rho G, right? So that's our matrix form of our expression. Yes, 0, 0. And now we have to evaluate the transfer function of PS to Q naught. So as you can see, but we don't have any variables which is Q naught. But Q naught, as you guys know, the outflow can be written from our from one of our variables HS. So what we do is we first evaluate the transfer function for HS and then we convert it to the appropriate form. So first of all, let's evaluate that. Let me add in another page so that we can have a look at this. Let's remove some of this, we don't need that. And let's cut this, put this on the top. And maybe let's shrink this a little bit because these matrix equations do get really large. So now what we have is HS can be given by the determinant of basically these three terms over here. Oh. Okay. Let's shrink this a little bit more. Sorry for that tiny font size, I'm just trying to fit these things in. And maybe a better way to do it now would be just to write it down. So we have PSS 0, 0. So that would be our numerator. And this would be divided by the determinant of the entire coefficient matrix A. So I'm calling, let's say I'm calling this entire matrix A. So this would be determinant of A. And once you simplify this a little bit more, you will see that the numerator turns out to be 1 by R1 PSS divided by the determinant of A. And we also know, so now we essentially have HS by PSS is equal to 1 by R1 times determinant of A. And if you were to calculate the Q naught to PS, you guys know that HS is also equal to or rather Q naught is equal to Q naught S would be equal to rho G HS divided by the resistor R2. So this is again coming from the flow that was going out of the second valve, right? The expression that we had for Q out. So it's the same expression that we have just taken a Laplacian for. And using that, we know that HS can be written down as nothing but R2 times Q naught S divided by rho G. So we plug that in to our expression here. Thus we finally would have Q naught S is equal to Q naught S by PS is equal to nothing but so we would have rho G come on top. We would have R1 2 times 1 by determinant of A. So there you have it. That is our final answer for part B.